term which we liked, which was the notion of why we're making a step in the right direction. And then we had some extra error terms, which were these systemic error types of things that told us we converge at a geometric rate until we get to about how large the error term is, and then maybe we get stuck. But at the very end of the lecture, what I showed you is actually once you have an analysis for altering minimization, you can actually think about ways to remove that systemic error altogether just by a slight change in the decoding rule. So at first, I give you a very simple decoding rule, and then I give you a very slight change on it, which actually entirely removed the systemic error. And actually, one of the things that I was kicking myself for not emphasizing more at the end of the lecture was that, why are we actually doing this for analyzing altering minimization? It's a heuristic that you can suggest works, and lo and behold, it does work in the right generative model. But the point of analyzing these things, at least from my perspective as an algorithms person, is you want to be prescriptive at the end of the day. It's great to be descriptive, to take things that people know and love and use and figure out what makes them work. But you're hoping that by analyzing it, you can do exactly that and figure out a suggestion for how to actually improve them. So when you have simple heuristics, there's no reason to believe, if you don't understand what makes them work, there's no reason to believe you have the right version of them to begin with. So that's really, the main punchline from that work for altering minimization was that once we did have this framework set up for how to analyze them, we actually can, be prescriptive and change what we think is the right version of altering minimization. So in any case, the thing which connects most closely with, what we were talking about with like sparse recovery and sparse coding is not our next unit. It's actually matrix completion. But we're going to cover that at the end of the semester because I think it's probably the most challenging topic. It'll force me to actually introduce things like sum of squares and computational versus statistical trade-offs. So I'm really saving that. And what I want to tell you about for now is Gaussian mixture models. So over the next few lectures, we're going to talk about, we're going to introduce this problem of trying to learn the parameters of a Gaussian mixture model, given random samples. We're going to talk about a few different algorithms for doing so. There'll also be yet another place where we can talk about a lot of the issues about how inference and algorithms and generative models relate to each other, and how you can get around computational intractability by thinking about the problem in a different way. So actually, Gaussian mixture models really have a long story to them. So it'll be a great way to think about, how the tools for statistical inference have changed over the years. In fact, over a century since this problem was first introduced. So Gaussian mixture models were actually introduced by Carl Pearson. Back at the very inception of statistics of the field. So he introduced Gaussian mixture models because of some particular applications he had in mind to biology and evolution. So I'll get into that in a minute. Anyone heard of Pearson? What's he famous for? Anything you know?
Neyman-Pearson test or something?
Yeah,
like that.
Yeah.
I don't remember what it was.
So that's the, but there's one other one that I was more expecting. Correlation, yeah, that's one of them. Any?
Separability.
What's separability? To be fair, he's famous for so many things that I don't know all of the things he's famous for. There's another really good one to know. Anyone else?
Hypothesis testing?
Hypothesis testing, yeah. In fact, there's a particular test that he was famous for. Anyone heard of the chi-squared test?
Yeah.
So that's Pearson's chi-squared test. So he was actually, one of the founders of statistics. And I think it's actually really interesting that, the way to understand how statistics came up with his definitions, this is my personal opinion, is almost understand some of the feuds that happened at the founding of statistics. So Pearson and Fisher were from very different schools, and you can see a lot of their differences of opinion sort of manifesting themselves in the different definitions that they studied and the different types of problems they worked on. In fact, if you dig a little further into Pearson, when I wrote some paper on this, I did, and then you get to some more unsavory things. He was also a eugenicist, which is rather unfortunate, so that's when I stopped looking into it, but good to know. So in any case, with this in mind, so he introduced things like the chi-squared test, Pearson's correlation coefficient, and so on. One of his original famous examples was called the Naples crab. And so what happened was that there was a colleague of his who, what he'd done was he'd taken painstakingly thousands and thousands of samples from these Naples crabs on this guy's vacation. And what he did was he measured some physical characteristic of each one of them. So in his case, he measured something like the size of the forehead of these crabs. And so Pearson had a copy of this data, and what he expected from sort of very biological first principles was that he believed that the data would be well approximated by Gaussian. But actually the data he observed was not a Gaussian. So if you plot this data, here what I'm doing is I'm looking at the number of species, so the number of specimen, versus the forehead size. And so this is a sort of smooth approximation of the types of data he observed. It was a little bit noisier than this. But what he expected was that it should be a Gaussian. So let me remind you what a Gaussian is, because we're going to use it throughout today. So remember that a Gaussian, which I'm going to always use this notation for. So this will be the PDF of a Gaussian with mean mu and variance sigma in one dimension. And it's just given by the following formula. So there is a normalization to make it integrate to 1. But the important thing is that it's centered at the point mu, and it decays exponentially around that based on what the sigma squared is. So the larger sigma squared is, the further out you have to go in order for it to decay. And wherever mu is, that's the center of this Gaussian distribution. So there are a lot of physical characteristics which are indeed measured by, are well approximated by Gaussians, because a lot of times you think about this physical characteristic as being some sort of sum of independent random variables for which genes you contain. But what he got was clearly not a Gaussian because it wasn't even symmetric around its maximum value. So he was quite puzzled by this, but what he offered as a suggestion, which is what prompted him to introduce Gaussian mixture models, was that he suggested that it could actually be explained as a mixture of two Gaussians, and that the Naples crab was not one species, but was two. So that's what we'll be interested in today. Let me try and formalize this in a second. Is really this question of if we're given random samples from what we believe to be a mixture of two Gaussians, can we learn its parameters? So are there any questions about this? So let me define what a mixture of Gaussians is precisely. So what does it even mean to learn a mixture of Gaussians? So a mixture of two Gaussians, let me define it through its PDF. So it has PDF, which is just a convex combination of the PDFs of two different Gaussians with potentially different parameters. And this quantity right here, we're going to call the mixing weight. It just represents the overall population, what fraction of species 1 and what fraction of species 2. So of course, in all of this, we're going to constrain that W, this mixing weight, is between 0 and 1. Usually it'll be strictly between these two things. But that's the basic idea, is that a mixture of two Gaussians is a distribution whose density function is just a convex combination of two different Gaussians. And we can now think about sampling from a mixture of two Gaussians just by taking a coin, which is biased. So you flip some biased coin, whose probability of heads is W, and If it's heads, you output a sample from the first Gaussian. And otherwise, you output a sample from the second. So does the mixture model make sense? Are there any questions about this? It's a very simple model. And this is in part why Gaussian mixture models arise in so many different fields of study, not just in evolution, but you can also think about some of the other applications of mixtures of Gaussians. Can anyone think of something that could plausibly be modeled by a mixture of Gaussians, a mixture of two or more Gaussians? Height. So height is one of the famous examples here, because biologically your height is actually some sum of about 12 or more genes. But of course it depends on whether you're a man or a woman what the mean of this Gaussian is. And so you can think about the distribution of heights of the entire population, which is composed of the distribution of heights of men and of women as itself being a mixture of two Gaussians. Can anyone think of anything else that might be described as a mixture of two Gaussians? What? Class grades. I haven't decided that yet. Okay, so actually, but there are also physical models. So there are a lot of applications in biology and things like ecology where you have rainfall and so on. But what you can also do are you can do things like ideal gases. So if you have some ideal gas over a long period of time, then actually the distribution of velocities in an ideal gas will be normally distributed. And what happens when you mix a few different types of gases is that at the initial outset, before they start to collide with each other, you're actually going to get a mixture of multiple Gaussians. Now, there are also a lot of applications in things like machine learning. But one of the real distinctions about the applications in machine learning is that they're very high dimensional problems. So a lot of times you use a mixture of two or more Gaussians as some sort of model for well-clusterable data. So you hope that you have a bunch of data in very high dimensions because there are tons and tons of features associated with each of your examples. And you hope that different ways to classify the data are really because you can model that set of samples you're given as some sort of mixture of Gaussians. And that by fitting the parameters of mixture of Gaussians, you can hope to figure out where the different clusters are. So there are a lot of formulations for clustering problems. We talked about things like k-means clustering earlier in the class. But mixture of Gaussians are yet another way to put a distributional model on the problem in a way to try and extract what the underlying clusters are. All right, so in fact, what I want to tell you about, I want to tell you about Pearson's actual approach for this problem, because there's one more thing that Pearson invented, which is really famous for, is he actually invented what's called the method of moments. And it was for this particular problem. It was for this basic problem of given random samples from what we believe to be a mixture of two Gaussians, can we learn its parameters? So you'll see from the definition of a mixture of two Gaussians, what we mean by learning a mixture of two Gaussians is really just, can you learn the 5 underlying parameters that define what the PDF should be? There's nothing more you can learn about it than what the PDF should be. So in the best case scenario, what you're hoping to learn is you're hoping to learn the mixing weight, the first mean, the first variance, the second mean, and the second variance. And that was Pearson's question, so let me write it up so that it's clear. And then I'll tell you about Pearson's approach through the method of moments. So in this case, what I mean by learning the Gaussian mixture model is we want to learn what the right settings of these parameters are to exactly produce the underlying density function. You know, one thing that's important is that in general, we won't be able to learn which one is the first mean and which one, you know, we can always swap which one is component 1 and which one's component 2. So, you know, as usual, we have this issue that we really can't distinguish between two related Gaussian mixture models. Because if I switch which one's component 1, which one's component 2, and take 1 minus the mixing weight, I get exactly the same density function. So we'll only be able to learn the parameters up to this invariance. So are there any questions about that? All right, so let me tell you about Pearson's method of moments. We're actually going to prove that it works later on in the course. But for the time being, let me just state it as a heuristic. So Pearson's method of moments is based on the following key observation. So this is the key claim which we're going to use to describe Pearson's method of moments, was that, let's say, I take a sample from a mixture of two Gaussians. So here, f of x is as above. It's a density function which is associated with a mixture of two Gaussians. And what we're going to do is we're going to compute the rth raw moment. So why I'm calling this the raw moment is that these are not the centralized moments. So for example, when r equals 2, I'm looking at the expectation of x squared. So this is not the variance because I haven't corrected for what the mean is. But that's not a big deal because I'm looking at, for example, the expected value of x and then the expected value of x squared and so on. So this is just a more convenient basis for thinking about what the first r moments are. But the key claim in all of this is that this quantity, the expected value of x to the r, well, it's a function of the underlying parameters. After all, this f of x, the function that we create, this PDF, is itself a function of just these 5 underlying parameters: mixing weight, mean invariance, and mean invariance. But the key point is that analytically, if I compute what this should be, what this expectation is exactly, then in fact, this quantity is a degree r plus 1 polynomial in this vector of parameters, theta hat. So if we think about all of our unknown parameters as variables, then analytically, this is a polynomial in those parameters. And moreover, it's a somewhat low degree polynomial. So the way to think about this is, I'm not going to prove this for all of R, but let me just ask you guys to prove the first few. So what's the expected value of x sampled from a mixture of two Gaussians? The average of the means, right? So all it is w mu1 plus 1 minus w mu2. Does everyone agree with that? Right. What about the expected second moment?
The weighted variance but squared, maybe?
I don't want variance.
Well, the
No.
sigmas?
So you're on the right track that I should definitely, the same way I should just have an average of these two, right?
But the
Because
weights
all I'm
are,
doing,
but the weights are squared, maybe?
no,
Or something like that?
not quite. So it should definitely be, the same way that this computation works, just because I'm breaking it up into the probability comes from the first Gaussian, which gives me W times its, conditional expectation. and then I break it up into the probability it comes from the second Gaussian times its conditional expectation on the second Gaussian. So I can do the same thing for the expected square.
We need the variance plus the mean square.
Yes, perfect, and weighted, right? So what I would do is I would just do this. Perfect, right? Because this is the expected squared moment of the first Gaussian, and I'm just doing the same conditional trick, right? So really what this claim revolves around is just the statement that it's true for a single Gaussian. And then all you're doing is you're taking the average of what it is for a single Gaussian weighted by the mixing weight. That's all that happens. So as a bonus question, I'm impressed if anyone knows this, what is it for the third one? That didn't work? All right. Anyways, I'm just going to write this out, and you'll see why I'm not going to prove this. Okay, so for example, this is the expected cube. And you can go on. I mean, so you can think about this a few different ways, that actually the degree R moment of a Gaussian is related to Hermite polynomials. So you can explicitly write out what this polynomial is. You could look it up on Wikipedia, or you can prove it to yourself that it's a degree R polynomial always, just by integrating it and doing integration by parts. But you can see that as you go on, these expressions get much more complicated, but they are still degree R+1 polynomials. So that's the important fact. So now Pearson's idea is to use the analytic expression for what the moment should be as a constraint on what parameters fit his distribution. Right. So let me now describe Pearson's sixth moment test. And actually, let me define the expectation of x from f of x to the r as mr of theta vector. So this is just whatever this explicit degree R+1 polynomial is. Let me just create a name for it instead of having to write out these laboriously long polynomials. The other thing is, what I'm going to do is I need empirical approximations to these. And what you can do is, given a set of samples S, what you can do is you can take, for all x and s, you can take the empirical average of their rth moment in the natural way. So of course, what you have is that for any fixed r, as you increase the size of S, and they really do come from a mixture of two Gaussians, m tilde r converges to what this value should be when you plug in the true parameters for theta. So that's not hard. In fact, the number of samples you need, though, keep in mind it gets worse and worse as you take r larger and larger. So if you want to get some approximation to the mean of your distribution, you might need, in order to get epsilon close, the parameters are all in some reasonable window. You need like 1/epsilon squared samples. To get an approximation of the variance, you need a higher polynomial in 1/epsilon and so on. But the important point is that if you only consider R constant, then you actually can, in polynomial number of samples, have the property that with high probability, given enough samples, these are all close to what they should be. So here's what Pearson's approach was. So this is called Pearson's sixth moment test.
How does the number of samples grow with R?
Like 1/epsilon to the 2r. So you can prove it just by second moment types of things. I think that's the right noun, but it'll definitely be 1 over epsilon to the theta of r. So that's the way to think about it, is that it really does get bad for larger and larger r. So, what's going to happen, you do exactly what Pearson did in his paper. It's a really amazing paper, actually. So you gather tons and tons of samples. In his case, his friend gathered them on vacation. And then what you're going to do is you're going to compute m tilde r for r from 1 to 6. And then what he did was he solved for all simultaneous roots of this system from r equals 1 to 5. So is anyone surprised by something that I said here? This should bother you. This was in 1894. So he solved this system by hand. So as painful as the polynomials got for third order things, he worked it out to fifth order, and he solved it by hand. And he found not one root, but he reasoned about every simultaneous root and found all of them. So people, this was back when people wrote tough papers, and now we have like Mathematica and other things, so you should be fortunate. I mean, it's amazing the length of calculation in these papers. Now, so what he got, though, when he solved this system of polynomial equations, by hand, was he got some, not one solution, but a candidate set of solutions. So what he got was theta 1 up to theta t. I think in his case, he had 9 solutions or something like this. Now, each one of these is a vector of parameters, right? So it's a choice of how to simultaneously set the parameters, how to set all 5 parameters, so that together they perfectly explain your first 5 moments. So that was the intuition, was that you have 5 unknowns and 5 constraints. But these aren't linear systems, so we can't in general hope that they have a unique solution. They might have many, a multiplicity of solutions, theta 1 to theta t. So these are all settings of parameters which would perfectly explain the first 5 moments that he had empirically observed. Now, some of these things were, clearly the wrong answer. Like some of them, for example, might have a mixing weight which is not between 0 and 1. That made them necessarily not the right setting of the parameters. They might have a negative variance, which is also not allowable, just based on what they were as solutions to the system of polynomials. So he crossed them off his list, but he still had more than one candidate solution, which could explain the first 5 moments. So what he did was he chose among them based on the 6th moment. He'd only used the first 5 moments so far. So after he crossed off the ones, that were clearly not the right answer, what he did was he outputted whatever candidate solution So each one of these settings of parameters yields some analytic prediction for what the 6th moment should be. All of these things perfectly explain the first 5 moments. And you can just plug in each of those candidate solutions into m of 6 of theta and get what it thinks the 6th moment should be. And you just use the 6th moment as a tiebreaker, and you choose whichever vector of parameters yields an analytic prediction that's as close as possible to the truth, and you output that. Yep?
With all these different constraints on parameters of variance and value between 0 and 1, is it possible that you can do this test and get no that's valid?
Yes. In fact, so this is exactly segueing into my next point, which is that, so this is the 6th moment test. First, I want to make sure, does everyone understand the definition of the 6th moment test? Very simple, first thing you would think of doing. You gather samples, you compute the empirical moments, but now the method of moments, when you're thinking about what the empirical moments of your distribution tell you, you encode that into a system of polynomial equations. It's very natural in all of these things to do the low order moments, because those are the moments which you have up to the highest accuracy. But now there are a lot of issues with actually even proving any sort of bounds on this. So when Pearson showed it, it was a heuristic, right? I want you guys to answer what are the issues you might expect in trying to prove that this really does find the correct solution. So let's do that. So can you guys think of any issues with proving correctness? There's one that's easy and more immediate, but there's one that's a lot more subtle, which is actually the meat of the issue, I think. So, yep.
Is there a problem with the fact that there are all expectations and we don't know how concentrated they are?
Sure. Let me try and clarify this a bit that, at the end of the day, you're on the right track that, at the end of the day, we take a finite number of samples, so our empirical estimates to the true moments are not perfect approximations anyways. We do know that they converge, that they're very, very close, but we'll never have that they're exactly equal to what they should be. So the best case scenario, what we're hoping for this procedure is that if we want to learn the parameters of the underlying mixture within an additive epsilon, we want that we only need poly in 1 over epsilon running time and sampling complexity. That we should really run this with S as maybe 1 over epsilon to the 2r, or some such thing. So, but that's very close to the first issue. So can anyone state what you think an issue might be with the 6th moment test and proving its correctness? If there are no issues, someone should just prove it. No?
That a small error in one of the empirical estimates might lead to a huge massive.
Exactly. That's the easy one. There's but let me write that down. So you can think about it this way. Let me just clarify it, state it a little bit differently. So the first problem, which the first time we see systems of polynomial equations is really the thing that would bother me, right? This is what you would naturally think of as the biggest problem, is does perturbing a system of polynomial equations roughly preserve its solution? So why I'm saying perturbing is because we have this ability to take more and more samples. We can get all of the empirical moments as close as we can get them within an epsilon for any epsilon, provided we take 1 over epsilon to the 2r samples. So we have this ability to really drive down the error in our right-hand sides in the system of polynomial equations. Now, we talked about this issue for linear systems. So who can remind me what property of a linear system ensures that it actually is stable under perturbations? Condition number, exactly. So when we talked about, back in tensor decompositions, we talked about what are the conditions you need to prove that Generick's algorithm really does work when you're given random samples that are approximations to the moments, but not the true moments. And we said at the end of the day, what you need is that these underlying factors are well conditioned, because that's what allows you to say things like linear systems preserve their solution within the condition number, and allowed us to do things like matrix perturbation bounds, like Grishkorin's theorem, and study properties under which the eigendecomposition even is preserved under slight perturbations. But once you have a system of polynomial equations, what you're really asking is, what are the condition number properties of systems of polynomial equations? Is it true that when you make slight perturbations to them, that you don't have too big an influence on what the actual solution is? That's problem number one. There's actually an even more serious problem. So anyone think of what the more serious problem is? Let me just tell you that there are tools that you can use that analyze the stability properties of systems of polynomial equations. They all have this property that their stability depends very badly on the degree and the number of variables. That's inevitable. But in the system of polynomial equations we're talking about, the number of variables is finite. It's 5. And the degree is also finite. It's at most 7 when we look at the 6th moment. So that actually ends up not being that much of an issue, that you can use sort of black box techniques to analyze the condition number. But even perturbations aside, there's a more serious issue.
And in the worst case, it can be hard to estimate the real data given the real.
Yeah, that, I guess, gets lumped in a bit with problem 1, because the fact that systems of polynomials are not horribly conditioned, if you make them constant degree and constant number of variables, also goes along with the fact that there are algorithms for solving those things, that they're very intimately related things, like the algorithms are really based on the stability properties. So that's definitely true. Even if I gave you all of that, what if I put no errors in the problem, and I gave you an oracle for solving systems of polynomial equations? There's still an issue. This one's more insidious.
Is it maybe to do with uniqueness?
Yeah.
Maybe it's not.
Yeah, exactly. So implicitly in all of this, we're saying that the first 6 moments should uniquely determine the parameters of mixture. Why should that be true? So is every mixture of 2 Gaussians uniquely determined? Of course, this uniquely determined is up to relabeling which one is which component. Is uniquely determined by its first 6 moments. It's kind of surprising at first glance that actually this is the heart of the issue. That these techniques are actually, once you have that a system of polynomial equations has only the solutions you care about, we'll get into some of the tools from systems of polynomials later. But once you prove that, then you actually have black box statements about why they're somewhat stable. And actually problem 2 is really the heart of the issue. So we'll come back to that later. But I just want you to keep in mind what the biggest issue is behind with this. Are there any questions about this? No? All right. All right, so the other thing I want to tell you about is I want to tell you about some of the history of some of these problems, because it's a great way to really think about computational intractability and what we need to do if we're looking for algorithms. So as we just talked about, Pearson was the first to study this problem. He introduced Gaussian mixture models. And what he did was he introduced the method of moments. Actually, for this particular problem. But the way he did it, there were no provable guarantees. We're going to fix that, but we'll come back to that later. So the way he did it, there were no provable guarantees, and all he did was he empirically had a particular data set he cared about, and when he solved these equations by hand, he got a good fit. So his evidence for these things was purely, based on analyzing real data. Now Fisher is the other, big name around this time. Pearson and Fisher had a big feud, a philosophical feud even, because Fisher was the one who really introduced the information theoretic view for thinking about inference. So he introduced what's called the maximum likelihood estimator. So this is a very important estimator to know. So who's heard of the maximum likelihood estimator? Wow, all right. All right, well, I'm still going to tell you what it is. Because I want to tell you some of the properties of it, which are important to know. And it's important to know what properties it doesn't have. I think sometimes these things get lost in the definitions. So what you're really doing is you're looking for the vector of parameters in some feasible region which maximizes the probability of observing your given set of samples. So what I'm saying here is that you have your S samples. Now for each one, when you set the parameters, then you have a probability of actually generating it according to that mixture of two Gaussians. And all you're doing is you're looking for the set of parameters which maximize the probability of having generated your observed set. So now there's actually an issue with doing maximum likelihood without any constraints. Like, what if I allow this space H to be all feasible settings of the parameters? So I allow all mixing weights between 0 and 1, all means and all variances. Does anyone know what the issue would be with trying to even solve that optimization problem? Forget the fact that it's computationally hard. So the issue is actually that when we're given a set of samples, you'd be better off choosing one infinitely small variance Gaussian and putting it on one of the data points and using some finite variance Gaussian to explain all the others. So in all of these settings, maximum likelihood, what you have to assume is you have to assume that you're optimizing over some reasonable range of parameters. So really you need to do things like lower bound the variance in order to get guarantees for these types of problems. But one of the things which Fisher may or may not have proved, it's not so clear, is actually that asymptotically, that this estimate converges to the true set of parameters. So this is called consistency. That what you do is you choose the problem size as fixed, you take an infinite number of samples, and you ask in a limiting sense, does the maximum likelihood estimator, suitably constrained, correspond to the true parameters? In fact, there's an even stronger notion, which Pearson was really a proponent of, which is called asymptotic efficiency, which these days is a little bit of a misnomer because we should really call it asymptotic statistical efficiency. And what he showed was that, if you think about this estimate, whatever whatever it is, it's not going to be for some finite set of samples the true setting of the parameters, but asymptotically, it's going to converge at the fastest possible rate to the true parameters. So a lot of times that rate of convergence is called the Fisher information. So what's true is that actually, if you take the limit of this, what this looks like, it'll actually be well approximated by a Gaussian around the true setting of the parameters, whose variance is the Fisher information. But one thing that I really do want to emphasize, that this is the way that some of statistics and the original definitions in statistical inference were founded, was that you're thinking about the problem as if you're sample limited. So you care about getting the most out of every single one of your samples. You care about which estimator converges at the fastest possible rate to the true parameters. But there's a really serious issue with the way these definitions are set up, which is that they're all asymptotic. So they're all about what happens when you take the limit as you have an infinite number of samples, because they're really based on expanding the log likelihood and using a Taylor approximation. But you don't a priori know what the radius of convergence is around, for that Taylor series. So there's the issue that even though things like maximum likelihood are known asymptotically to be the best you can do, in terms of finite sample guarantees, in a lot of cases we really don't have them because of the asymptotic nature of the methods. Now, of course, the bigger issue is that maximum likelihood is usually NP hard to compute. for mixtures of two Gaussians, this was proved by Aurora and Canaan, that it contains hard problems like k-means clustering, which are even hard to approximate. But almost every case you see it, really maximum likelihood is hard to compute, especially for mixture model types of things. Are there any questions about this? Does this make sense? There's definitely something I want to emphasize, that a lot of the definitions in statistics are set up for asymptotic theories. So the other thing I want to tell you about, there's quite a lot of work on this problem. Let me sketch a famous result of Teicher. So, there wasn't too much work on this since then. But Teicher in 1961, what he proved was called identifiability. Namely, that if we know f of x exactly, we can determine parameters exactly. Up to the usual relabeling, we don't know which one's component 1, which one's component 2. So let me draw you a picture. This is actually not so hard to see why this should be true. But imagine we had some mixture of two Gaussians, which these were the two Gaussians. So imagine we have perfect access to the density function for this mixture. Anyone have any ideas about how we can learn the parameters from looking at this density function? Like, what if I gave you the ability to look at it in any value you want and perfectly get what f of x is? And my hint is you should look at the tails. So does this component matter in the tails? No, right? So if I go all the way out into tails, the key point is that the dominant behavior is based on whichever Gaussian has the largest variance. The difference in their means is swamped eventually by what their difference in variances are. And so what ends up happening is if you go all the way out in the tails, far enough out, then what you're saying is that this has essentially no influence. And based on the limiting properties of the distribution at the tails, you can figure out what the largest variance is, of two Gaussians. And then once you know its variance, you can figure out the mean of the largest variance Gaussian. And then what I could do is I could subtract off that density function, the Gaussian, and recurse on the remaining one Gaussian. So in this way, I could actually learn mixtures of any number of k Gaussians. This is called identifiability, is at least in the setting where you have an infinite number of samples and you know everything about the underlying density function, then you actually can learn the true parameters. Now, what we're actually going to care about is we're going to care about robust identifiability. We care about how much you can get with poly and 1/epsilon samples. Can you learn the parameters within an additive epsilon? So can anyone think of an issue with using this approach to try and get good algorithms? How likely are this? Oh, yeah.
I mean, all of our samples way out in the tail are going to be absolutely tiny, so we're not going to actually get
exactly.
the numerically.
If you think about it, exactly, right? So you're saying look at the incredibly rare events and use the very subtle behavior about what those really rare events look like to be able to extrapolate what the variance is of the largest variance Gaussian. So that's a big issue, is that the natural way to prove identifiability, the algorithms we're looking for actually have statistical guarantees which are not a priori obvious, is that we want to know how we can learn the parameters from the meat of the distribution, not the real tails, right? Or to make this point, to emphasize it in a different way, What you'd be telling Pearson to do is to wait for a crab whose forehead length is negative, so that you can then recover what the variance of two components is, right? Which doesn't make any sense. The other thing I want to tell you about, this is another sort of tool that you should really be aware of, and I want to introduce here formally. One of the really important works, more generally on this and other problems, was by this work of Dempster, Laird, and Rubin, who in 1977 suggested a really important heuristic for dealing with the fact that maximum likelihood is hard to compute. What they gave was called the EM algorithm, so the expectation maximization algorithm. Let me describe what that is, but you can think of it like alternating minimization on this really non-convex objective. The difference is that for mixtures of Gaussians, I really don't know any guarantees for the EM algorithm that don't require very, very strong assumptions on the underlying parameters. But let me now describe the EM algorithm. So what the EM algorithm does is it first initializes some estimate for the parameters. So W mu1, sigma 1 squared, U2, sigma 2 squared. And then it repeats the following procedure, which greedily updates the parameters. So what you're going to do is, for each sample in your set, S, you're going to calculate the posterior. The way to think about it is that you have some belief about what the underlying parameters are, and for any particular sample now, that gives you a posterior belief on what you think the probability is that it came from component 1 versus component 2. So in fact, what this posterior would be, this is really, you can think about it as being the probability X was sampled from component number 1. At least this is your belief about the probability. And what this would be is you just take a probability that you were generated from the first component, which is just evaluating the PDF at that point, but only taking into account the contribution from the first component. And you also have to weight by the mixing weight, because the smaller the mixing weight, then the less likely you're likely to believe that it came from component 1. And you normalize by the total probability of having generated that point at all. And now what you do is, once you've calculated the posterior, you also then, that gives you a belief about, for every point, which component generated it. It's like a fractional assignment. For each point, you have some distribution over the two clusters. But you use that distribution to now update your parameters. So what you're going to do is the new mixing weight, I'll use W prime to denote that it's the new mixing weight, is you're going to set it to be sum of X in S, Px, over size of X. All this is the empirical fraction of the points, the weighted fraction of the points that you believe came from component 1, according to your current beliefs. You're going to update your mixing weight. Now you're going to update your mean too. So for example, the first mean, which you would update it to be, is you would just take sum over X of Px times X divided by w prime, because that's the sum of the px's. So it's a fractional weighting of the average values of these x points. And you're going to do the same thing for sigma 1 squared prime. That, again, you take this weighted average. Now the difference is that here I'm going to use the new setting of the parameters for the mean. So I've denoted it by mu1 prime to denote that it's the new value. And again, you average it by w prime, and so on for also the parameters mu2 prime and sigma 2 squared prime. And then what you do is you update all of the parameters. So w becomes the new value for w prime, mu1 becomes your new value for it, and so on. So in this way, all you're doing is you're alternating between updating your beliefs about the posterior given what you think are the true parameters, and then using those conditional probabilities to update what your parameters are for what you believe the mean and variance are. So this is a step which, you can think of it like alternating minimization, that we have this simultaneous optimization problem over many parameters that makes this maximum likelihood problem non-convex. But what you're doing is you're greedily updating the parameters so that you do better and better. You can think about it like when we talked about k-means clustering, how once you decide what the clustering is for the points, you have no choice but to choose the mean to be the average of those points. And in that way, you keep alternating between updating your centers and then updating your classification each time making progress. But the bigger issue is that these types of things really can get stuck in local minima. And there are only some very weak guarantees for this EM algorithm for mixtures of Gaussians. And the very last thing that I want to talk about probably for today is I want to start to talk about some of the provable guarantees. So these things were really introduced by Dasgupta, who started this goal of having provable guarantees for mixtures of Gaussians. And I want to tell you about his approach. We're going to analyze approaches like it in the next class. And then eventually we're going to go back to the method of moments and actually show that Pearson's approach works in general. Are there any questions?
Yes.
Yeah.
So which is the E step, which is the M step?
I always forget.
The E step is the posterior. The M step is updating the parameters.
I guess it goes E and then M. Thanks. Okay, so let me tell you about Dasgupta's approach. So, in this really important paper of Dasgupta in '99, he introduced the problem of actually, trying to provably learn with a polynomial time algorithm the parameters of mixture of Gaussians. Now, one of the distinctions is that he was much more interested in very high-dimensional problems, where his approach was actually based on clustering. And it only really makes sense to consider his approach in very high dimensions. But let me tell you what it was. So his approach was based on clustering. So the outline for his approach is what you want to do is you want to somehow, some way, cluster S into S1 and S2 based on which component generated which sample. So the key point is, the same way for things like k-means when we talked about it was the hard part is getting the partition right. The same way what Dasgupta is going to hope is that in the setting of parameters he'll be interested in, purely in the high-dimensional problem, that somehow you'll give an algorithm which, with high probability, is actually going to be able to partition S into S1 and S2 based on which of the two components generated the different points. Now the key point is that once you've done that, this is where all of the work is, then the rest of it is immediate. because what you're going to do is you're going to output the empirical averages for the two different clusters, and those will be good estimates for your parameters. So we're going to suppose for the moment that we can do this. We're going to come back to this in the next lecture. But what we're going to do is we're going to set W hat, our estimate of W, equal to the fraction of points which go in S1 of the total. We're going to set, mu1 hat, for example, to be 1 over S1, summation x in S1 of x, and so on. So actually, let me write it out for hat 1 squared. So these are just the empirical mixing wave. This is the empirical mean of the first cluster. And this is the empirical variance of the first cluster again. And so the key point which all of this is relying on is just the fact that if you really could do step 1, then the fact that step 2 works is immediate. It's like saying, if I have enough samples from a single Gaussian, why should its empirical mean and variance converge to what they truly are? So let me just state what that fact is. But then what we're going to do is we're going to, this entire discussion will really be about clustering methods that Dasgupta introduced and what some of their limitations are, because we're going to get around some of those limitations, maybe in 2 lectures' time, by analyzing Pearson's approach. So the key fact that Dasgupta is sort of implicitly using here is that if the mixing weight is between epsilon and 1 minus epsilon, so you have some lower bound, but obviously if you never get a sample from the first component, you can't estimate its parameters. So you need to assume that at least there's some lower bound on the mixing weight so that you get enough samples from that component. And it'll also be easier just to think about some normalization guarantees. So let's assume that all of the parameters we're looking for are at most 1 in absolute value, so we've scaled the entire mixture, so that this is the scale on which we're learning. Then, what's true and not hard to prove is that if S is at least log 1 over delta over epsilon squared, and S1 and S2 are correct, so they really are the partition into which component generated which, then with probability 1 minus delta, we have that W hat and W are at most epsilon apart, and same for all of the other parameters. That we really do learn them epsilon close. So that's the point. Okay? Is that once we assume these normalizations, we're in good shape. So the last thing that I want to tell you about today is actually that, really step 1, you should be a bit worried about that. So can anyone think of a problem with even trying to do this? I mean, it makes sense in high dimensions, but in low dimensions, it actually doesn't make too much sense.
You can, any point in the space can be from any one of the 2 sources.
Yes. And even more quantitatively, the issue is that in low dimensions, the only way that you could hope to do this, with high probability, is if the 2 components are extremely far apart, and that once the components really do overlap, even information theoretically, you can't hope to do that. So, some of the first guarantees were really based on clustering, and we're going to be talking about eventually are about how the method of moments allows you to learn the parameters even when you can't hope to cluster. But let me first just try and corroborate this idea that you can't really cluster. Is there a question?
How far does it not?
So let me quantify that now. Is the way that I'm going to do this. The way that I'm going to do this is we're going to return to Pearson's original drawing, and we're going to talk about, what are the limitations, even information theoretically, about clustering. So I think that'll address your question after that.
And quick
Yep.
question. I don't know if I am understanding the conceptual difference of high dimensions. Like, why is it what's the issue between considering low and high? Can you emphasize that a little more?
Yeah, let me actually get to that in a second,
Yeah,
because
sure.
the types of things that you need to be true about the mixture in order for step one to make sense can still be true for interesting mixtures in high dimensions, because interesting mixtures need not overlap much for their components. But in low dimensions, what you're actually requiring is that the components be so far apart that you can just eyeball where the different humps are. You're really assuming that it's a bimodal distribution, which is not, the original set and stuff, right? So let me couch this in an actual discussion of, Pearson's data. So let's consider Pearson's data one more time. And remember, what we had was this density function, which was not symmetric around its maximum value. And what we did was we took a mixture of two Gaussians that looked like this that could explain the density function. Now, what I claim is that the fact that there is this overlap region between them is what implies that we actually can't cluster the points, even information theoretically. Good thing about it is, even if we knew the parameters, we wouldn't be able to figure out how samples in this intersection region, whether they came from this component or from this component. So one way of intuitively thinking about this is let me describe it informally first. Imagine I'm trying to sample from this mixture of two Gaussians. One thing I can do is I can draw a box around it. Here I'm sort of truncating the density function that's too far out. And what if I throw a dart at this now? So if I throw a dart, what I'm really going to do is I'm going to, in the case where it lies above this yellow curve, I'm going to ignore that dart. But when it lies beneath the curve, I'm going to output that sample. That's another way to think about generating a sample from the underlying density function. But now we can think about that underlying density function according to this yellow function as really being an average of these two functions. And what we can do is we can actually think about throwing a dart, and if it lands in here, we actually don't have to decide which component generated it. We can do it lazily, and we could never decide which component generated it. So that's essentially what I'm going to tell you, is I'm going to tell you a rule on how to actually sample from this mixture of two Gaussians in a way that for some of this overlap region, you don't even have to decide which component generated it, but it really is a faithful sampling from the original mixture. So that's the sense in which the overlap region is really the issue in assumption, in order for step one to work. So in high dimensions, you really can have mixtures that, because they're in high dimensions, they don't overlap much. And you really can take tons of samples without being confused ever. But in low dimensions, the only mixtures which don't have this overlap region are ones where the two components are extremely far apart. Yep.
But on the other hand, the mixtures, they have so much overlap that you really can tell. I mean, on the other hand, who cares, right? If you're using that.
That's a good question, right? Let me put it this way, right? So if I can learn the parameters, it's an excellent question. If I can learn the parameters, it means that when I take a new sample, I can compute with the Bayes optimal cluster. As in, that means when I take a new sample, let's say I learned the parameters perfectly, I can actually compute the posterior distribution on which component generated. So it'll tell me that I don't need the property that every single sample has to be completely unambiguous about which one it came from, but you can still have the fact that a very large fraction of your sample space actually really does have a fairly unambiguous way to label it. So here, when I sample from out here, I'll know which component generated it, roughly, and same for here.
I meant like even if you cluster the data, if the distributions are so close together, it probably won't matter. I mean,
Oh, in terms of learning the parameters. That's a more subtle issue because it depends on how you misclassify. If you really were an unbiased misclassifier, then that would be true. But that's part of the reason why I don't know whether alternate minimization works for these types of things, is it's not necessarily an unbiased class, error in which one it misclassifies. All right, so in any case, let me tell you what I'm really describing is a new sampling procedure. Remember that the old sampling procedure, the natural one, was just this thing where we took a coin, which was biased, which was heads with probability W, we flipped it. And if it came up heads, we took a random sample from the first Gaussian, we output that. And otherwise, if it came up tails, we took a random sample from the second Gaussian and output that. That's the natural way to think about sampling from mixture of two Gaussians, because it's explicitly true that its density function is a convex combination of the two constituent components. But let me give you a different way to think about sampling procedures. So this is a correlated view on sampling, which gets used in a lot of places, so it's worth talking about. And just so that we are on the same page, the total variation distance between two PDFs, P1 of X and P2 of X, is a measure of how much they don't overlap. So it's denoted by dTV, P1 of X, P2 of X, is just half times the integral of the absolute value of P1 of X minus P2 of X dx. So the total variation distance is something that's between 0 and 1. So the largest it could be is 1 if the supports of P1 and P2 were entirely disjoint. Then what you're really doing is you're integrating something which, absolute value is 1 and absolute value is 1 on the negative side. And you take this half to normalize total variation so that it's between 0 and 1. And when total variation is 0, then what you're really saying is they're the exactly same density function. Was there a question? No? All right, so this actually is going to be related to the overlap region. So what we're going to do is we're going to let n3 of x denote the min of n1 of x and n2 of x. So here I'm using a shorthand that n1 of x is really n of mu1 sigma 1 squared of x, but I just mean component 1. So you're going to take the entry-wise minimum, so it really is the sort of intersection region between them. And the sort of fact that we're going to use in this new sampling procedure is just that the integral of n1x dx over all of space is actually 1 minus the total variation distance between n1 of x and n2 of x. Let me set this entire thing equal to p. So that's the point, is that the total variation distance of 1 means you have no overlap region, and 1 minus the total variation distance is just quantifying what this overlap region is. So this is just a measure of how much they overlap. And now what you're going to do is you're going to flip a biased coin, where the probability of heads is p, and if heads output a sample from n3 of x renormalized by p, because its total integral is p, so I'm just normalizing it so that it integrates to 1. So all I'm doing is with some p probability, I actually do land in this overlap region, and I don't actually have to decide which component generated me, but I just sample from n3, and that gives me my random sample. The rest of what I have to do is I now have to sample from the remaining thing in such a way that my overall sampling really is a faithful sample from the mixture of two Gaussians. That's all I want to do. And so now, else So if you ended up with tails for this first coin, then what you're going to do is you're going to flip a new biased coin. Where the probability of heads is based on the mixing weight. And if it's heads, you're going to output a sample from n1 of x minus n3 of x all over 1 minus p, so that it's renormalized. All you're doing is you're taking this blue region minus the overlap region and renormalizing it so that it really does integrate to 1, and you're choosing a sample with it. So conditioned on you not being in this region, both density functions assign the same probability to this region. Conditioned on you not being in this region, you now have a probability W still of landing in the first component, and 1 minus W of landing in the other component. And finally, the last else statement is you sample from n2 of x minus n3 of x over 1 minus p. So only if it went tails you do this. Are there any questions about this procedure? So the simple fact that you can just check is that this procedure outputs a sample, a fair random sample from f of x. So this is really a faithful way to sample from the underlying mixture of two Gaussians. This is a very common technique that total variation distance, or more precisely 1 minus total variation distance, is actually a measure. You can think about it as a measure of how well you can sample from two different distributions in a correlated way to make them agree as much as possible. If you have a lower bound on the total variation distance, then you have a lower bound on how much they can agree, but this is the procedure that always achieves it. It's this type of correlated sampling where you're really throwing darts in some box, and when it lands in here, you're correlating which sample came from blue and which sample came from the red piece in such a way that you agree. And in this case, we're using that fact to say that for those samples, we don't even information theoretically have to decide which of the two components they came from. So the way to think about this is that step 1 cannot possibly work in low dimensions for interesting mixtures, because once you have like a quarter overlap, it really means that every fourth sample, you're going to get a sample which you really can't decide. It's a coin flip which of the two components it came from. Yet in high dimensions, there will be interesting settings where they are that far apart. So that'll be the clustering versus the method of moments kind of approach. So we'll get into that more later. The next lecture will go through Dasgupta's approach, which is pretty simple. Actually, we'll go through an approach of Aurora and Cannon, which gets slightly better guarantees, and I think is even simpler. And then we're going to discuss some of the problems in density estimation and parameter learning, and think about which one is harder than which, and what sorts of things are lower bounds to what. And then finally, we're going to talk about the method of moments. We're going to analyze it through the heat equation. We'll go back to Pearson's original approach. And then finally, we're going to do an abstraction of it through algebraic geometry. Don't be scared. It's not that hard. But we'll see when we come to it. All right. So thanks. And if you have any questions, let me know.
So Anchor, the concept is that they overlap and you get useless samples in low dimensions.
So the point is that this sampling procedure, imagine I annotated it with, not only do I get a sample from my mixture of two Gaussians, but I even annotate it with how I ran this procedure. So I tell you, what the coin ended up here, what the coin ended up here. That's only giving you more information. But the point is that when I go to this step right here, you don't actually know which component generated it, because I can hide that flip from it. This one, the sample you get from here, it really is probability W from the first component, probability 1 minus W from the second component.
So I guess this is the worry that I'm having. Let me think how to phrase it. Well, there are two things. let me say them before you address each one of them. One, in this framework that you put, like this sampling procedure that you wrote, I don't really see how the dimension is there explicitly, how it's part of it.
It's not.
It's not.
It's not. What I'm saying, though, yeah, that's a good point. Maybe I should have clarified that. Is that in order for a mixture of two Gaussians to have this property that you can cluster it, you need that the total variation distance is 1 minus little o of 1. That follows from this.
Okay.
If you're taking some super constant number of samples, you need that the total variation distance is 1 minus little o of 1. That any hope of being able to run this procedure. But what I'm saying is, in low dimensions, what it means for a mixture of two Gaussians to have total variation distance close to 1 means that they're just physically far apart, and that they have two humps, right? But in high dimensions, it's there are still mixtures of Gaussians that are interesting even though they have almost no overlap. It's the high dimensional part that makes it challenging, not the low dimensional part. That's all I'm saying, is that any such procedure like this is implicitly a lower bound that the total variation distance, that the overlap region should be vanishingly small, because you want that no samples come from that region. But I'm saying that there are interesting things you can do in high dimensions, like what we'll see next time is that if I have two different Gaussians, which the variance, if it's like sigma squared, the typical point, if it's that center to the origin, would have Euclidean norm root n if it has unit variance in every direction. And actually, even if two different Gaussians, their distance from each other is n to the 1/4, their total variation distance is still close to 1. So that's weird, is that even though they're root n size balls, their distance from each other can be n to the 1/4 before they have heavy overlap. And that's just an artifice of like high dimensional geometry that that the balls don't have to be disjoint for them to not have much mass in common.
Okay.
That's what I'm saying.
Okay. Cool.
So that's counterintuitive, but that's the property which is definitely, but that's the property of high dimensional, which is not true low dimensional. The reason that Dasgupta's things are interesting is because you have those weird properties in high dimensions, but if you took their guarantees and what his procedure is trying to do and asked it for low dimensions, it wouldn't be interesting because the two components really would have to be far apart.
Okay. Another quick question, and these results that you're telling me about, this intuition that you're telling me about, the dimension, does this, it seems to be kind of special to having a mixture of size 2. Does it? No, it's not.
No, not at all.
So everything that we're talking about kind of generalizes to more
except
mixtures?
for the method of moments will get much worse as k gets larger. Dasgupta's things will not get worse as k gets larger. But the flip side is that method of moments actually does have to get worse as k gets larger in low dimensions, because this is what I'll talk about next time.
Okay.
But the guarantees that you get are optimal. There really are two different mixtures of k Gaussians that have very different parameters that produce almost the same distribution as k gets larger and larger. That's not true in high dimensions under Dasgupta type conditions.
Okay.
So that, it's counterintuitive. I don't know what I can tell you other than.
I'll think about it and I'll see if everything solidifies.
Yeah, that sounds good. I don't know how to get intuition for the high dimensional things other than to just do them.
Yeah.
The calculation is very short for these things, for especially like the Aura Kanan version of it. But that doesn't make it any less
weird,
mysterious. Like Dasgupta's separation, it's kind of funny. Like he had this paper, but he had really suboptimal guarantees, even though he was the first one. Because the setting he was interested in, the balls really were disjoint. But Aurora and Kanan realized that in order to get this type of thing to work, that you don't need them to be disjoint. You just need them to have small statistical distance from each other, or large statistical distance from each other, and that happens even when they're n to the 1/4 separated, even though the radius of the ball is n to the 1/2.
Okay. Cool.
So I don't know how to tell you other than you do the calculation and it's true. it's one of the pathologies of concentration measure.
Mm.